Okay. So, we have talked about this coherent and non-coherent demodulation. It's part of the receiver circuitry. Okay. We have already talked about that if we have to do coherent demodulation, we need to extract the carrier, and what we will be trying to prove today, if that carrier recovery, means how important that carrier recovery is. If there is some error in the carrier recovery, what kind of detrimental effect it will have in the recovery of the signal. So, that is something we will try to exploit today. So, let us first see for DSB signal. So, let us say this is my DSB SC, which is nothing but MT cos omega CT, right. So, that is a typical DSB signal where MT is the modulating signal, band limited of course, it occupies in baseband up to bandwidth B, and then we have chosen a carrier which is omega C much bigger than that B. Okay. So, that is the DSB signal. Now, let us say what I will be doing, I will be locally generating a carrier. Okay. So, to demodulate it, first I will take it from the channel through antenna and then locally generate a carrier, whichever way I get that carrier. Let us say I get that carrier, I will multiply with this carrier, right. So, generally my demodulation process is something like this: DSB SC T multiplied by 2 cos omega CT. Okay. So, I multiply by this and then pass it through a low pass filter. This is what we do. Low pass filter which has a bandwidth roughly or cutoff frequency at B. Okay. So, this is what we do. But let us say this carrier that I will be multiplying with, it is not completely asynchronous. Let us say that has a phase offset of theta with the incoming carrier. Okay. So, let us say that is happening, that I have probably detected the frequency very nicely, the frequency is completely asynchronous, but the phase there is an offset of theta. Okay. But that is the carrier I am generating, so I will multiply with that carrier. So, what do I get? Okay. So, I can replace this by this, so I will get MT, 2 comes over here, cos omega CT into cos omega CT plus theta. So, that is 2 cos A cos B, so it should be cos A plus B into cos A minus B. Okay. So, I can immediately write MT, this is cos A plus B means cos omega CT, sorry 2 omega CT plus omega CT, 2 omega CT plus theta, and plus cos this omega CT plus theta minus omega CT. So, that should be theta, right. Now, I will be putting a low pass filter. So, this term will be cancelled because that is at frequency 2 omega CT, 2 omega C. So, I will be cancelling out this term, the rest of the term after demodulation I will be getting MT cos theta. Earlier when it was fully synchronized, there was no phase offset in the local carrier, I was getting only MT, that was good. Now, I am getting MT into cos theta. Okay. So, whatever offset we have, this is not a time varying term as you can see. So, basically if there is a phase offset, I get almost MT multiplied by a constant term. So, the message signal will have similar means undulation in time. Okay. So, the pattern of the message signal remains the same, it is just get modulated or sorry it just get multiplied by a constant term which is called cos theta, where theta is the offset. The problem with this is, what is the maximum value of cos theta? That is 1, but I have a chance of getting 0 over here. Suppose that theta offset is pi by 2, then I get 0. So, what do I get? I get nothing. So, there is a danger of huge attenuation if I have a phase offset. I do not know, that phase offset will be random, right. If somehow I choose a phase, means I get a phase offset of pi by 2 or around pi by 2, I will have a huge offset, means huge attenuation of the message signal. The message signal pattern is not getting changed because it is getting multiplied by a constant term. So, there is no problem in that. Message signal pattern is still remaining the same. Only thing is that unnecessarily due to my demodulation there is a attenuation term which is coming up. Okay. If my phase offset is near to 0, I know that not much attenuation will be happening, but if it is near to pi by 2, I have a big problem. Okay. My message signal will strength will go down heavily. So, this is one problem if there is a phase offset. Now, let us see if there is a frequency drift. Okay. So, I will again have phi DSB okay, which is now will be modulated, sorry, this is already modulated signal, I get that. Okay. Now, what should be means what we will be doing, we will be now demodulating it. Okay. So, while demodulating I will be again multiplying by the local carrier. Let us now say this is modulated with omega c, but this local carrier has a frequency drift. So, it is means I could not track that frequency. So, I get a delta drift to the frequency. So, let us say omega c is the targeted frequency, but I get omega c plus delta or minus delta, whichever way you take, and there is no phase shift. Let us say if on top of that there is phase shift, there will be additional effect, we know already what will happen if there is a phase shift. Let us say phase there is no drift, but frequency I could not track completely. So, there is a drift in frequency. So, now I can write this as mt cos omega c t into cos omega c t plus delta t, right, and the 2 term is there. Again I will put cos a into b. So, it should be mt cos a plus b. So, that should be 2 omega c t plus delta t plus cos delta t, right. Let us say now what will happen, there is a frequency term at mt modulated by some very small frequency drift, because whenever I am tracking the carrier I will not have huge drift, I will have a small drift. So, there will be a small shift, a little bit of shift in the frequency. So, there will be a small drift of that. In frequency domain if I wish to track that, so what will happen, there will be a means it will not come as mt, there will be a small drift of that, right. So, it should have something like this. Okay, so, there will be a delta drift and the other part will actually go into 2 omega c plus delta and minus 2 omega c means minus 2 omega c minus delta. Okay. So, that is where it will go. If I put low pass filtering now, it will just take this thing, rest of the things will be gone. So, I will be not getting this, I will still get this, which is nothing but mt cos delta t. I should not say delta t, it is delta into t, right. Now, this term is no longer a constant term. Okay. What it is actually, the mt is now getting a modulated term with cos some small frequency delta into t. So, this will distort the signal. So, frequency drift is even more detrimental than the phase drift. Phase drift, my message signal was almost similar, okay, and I was getting something over there as long as the phase was not going near to pi by 2, because then the attenuation, it was just an attenuated signal and the attenuation was not very big. Okay. So, that way I was safe, but here what is happening, my message signal is now getting modulated. Means whenever I demodulate, I expect that I should be getting message signal, but it is no longer the message signal. It has some modulation on top of this, which is modulated by that delta. Okay. The problem with this is, as you can see in the spectrum, because this delta is small, so there will be a small drift only. So, you will never be, so this is centered at delta and this will be centered at minus delta. So, the positive shift and negative shift will superimpose and they will actually generate a different kind of signal or different kind of spectrum, which will completely change the overall signal quality, and I will never be able to separate that out, because a higher modulation will always keep the signal shape intact or spectrum shape intact, but this is a lower modulation, so they get overlapped, the negative half and positive half gets overlapped, and I get something which is completely different. Okay. So, I will never be able to recover my signal back from this if this happens, because I know that that delta will be smaller, and however small it is, it will start distorting the signal. Okay. So, that has a huge detrimental effect in my demodulation. So, now I am just telling this because now you can appreciate why carrier recovery is so important and why carrier phase and frequency synchronization is so important. Without that, any coherent detection is of no meaning. Okay. Now, let us try to see what happens if I have this quadrature amplitude modulation QAM. So, let us say I have phi QAM t, which is m1 t cos omega c t plus m2 t sin omega c t. That is what we have said, that will be this. Now, while demodulating, I have to demodulate it. Let us say I want to just demodulate this m1 t. So, what I have to do? I have to multiply with a local cosinusoidal. Let us say that has a phase drift. So, I will be multiplying this phi QAM t with 2 cos omega c t plus a drift of theta. Okay. Let us say this is my x1 t. What do I get? So, it will be m1 t with 2 cos omega c t into cos omega c t plus theta, right. I get this plus m2 t 2 cos omega c t plus theta into sin omega c t. So, all we have to do is cos A cos B and cos A sin B. So, we put the formula of that. So, we will be getting m1 t cos theta A minus B, if this is A and this is B, plus m1 t cos 2 omega c t plus theta, and we will have m2 t sin 2 omega c t plus theta minus m2 t sin theta. Fine. I will be passing it through a low pass filter. These two terms will be gone. What do I left with? m1 t cos theta minus m2 t sin theta. Earlier for DSB-SC I was getting this, right, which was okay because cos theta is a constant term. Now what I am getting? I am getting this signal, but a spurious signal coming from here also. So, now because I have modulated it in such a way that they are actually co-occupying the same band. So, while demodulating, if I have a phase drift, I will have interference coming from the other signal. This is more detrimental. Earlier I was just getting a attenuated signal. We have told that there are no free lunches. You got a very nice frequency or bandwidth response by QAM, but if you have a drift in carrier for DSB-SC, you just had some attenuation, whereas for this one you will have a interference term coming from other signal, that you cannot do anything right now because they will be all mixed in the baseband and you have no way to actually demodulate them any further. Okay, so, it will just interfere your signal and it will corrupt your signal. So, this is the problem that QAM will have. which again you will see that our SSB will not have that. SSB will not have probably similar problem, but QAM will have a bigger problem coming some amount of interference from other signal. Okay. So, after knowing this, that the importance of carrier recovery and importance of not having any phase or frequency drift, and which particular modulation scheme suffers from phase or frequency drift in what extent. So, after seeing that, let us try to see if for VSB or SSB signal, if we wish to actually demodulate it, sorry not demodulate, we wish to get carrier back, what will be the associated problem. Okay. So, before demonstrating that, let us try to see how do I actually get a carrier back from a DSB signal, a double sideband modulated. So, let us say phi DSB SC signal, which is nothing but MT cos omega CT, right. This is my DSB signal. So, what I can do, this MT cos omega CT, I wish to take the carrier. So, this will be, suppose this is my MF, I do a modulation, it goes over there. Okay. So, it has all the frequency term. If I can put a very narrow band pass filter centered around that FC, whatever I will be getting, that will give me means the frequency term almost. Okay. The problem is with this particular method, if you just say that anyway this has been modulated with carrier, if I put a very narrow band, I will be getting my carrier back. This is something I should be getting, but that has some danger. First of all, to put a narrow band pass filter, you need to know the frequency. Okay. Roughly probably you will be knowing the frequency, but you might not know it exactly. So, you will have to put at least some amount of bigger band over there, but that is not as detrimental as the next one I will be talking about. Suppose this is a voice signal, what will happen? Will it have any DC value? No, the spectrum will look like this. Once I modulate, there will be nothing over there. So, around the carrier I have nothing. So, I put a band pass filter, I get 0, I will not be able to detect any signal. So, even though I know there is a carrier involved in it, but somehow the carrier is evading me, I am not able to get that carrier, right. So, what I can employ over here is something like this. I have this signal, right, this MT cos omega CT. Even if this has no value around WC, can I somehow generate something around WC or omega C? What is the chance of doing that? Let us put this circuit, which is a squaring of it. Okay. So, let us have MT cos omega CT. I square it. So, what do I get? Here I will be getting m square T cos square omega CT, right, which I can write as half m square T plus half m square T cos 2 omega CT. Okay. If it has some phase, that also will be tracked over there. So, I will get this. Now, if I put a band pass filter, this will be gone, but for this one I have now a better guarantee of getting something, because what is happening, I am now actually, suppose it was not having any DC term, it was having some spectra which was devoid of any DC term or around that DC term. Now, this is my MF, what I am getting over here is m square T. In frequency domain, what will happen? That will get convoluted, right. So, if I convolute this signal with itself, what will happen? It will have the highest peak around 0. Okay. So, whenever I convolute this signal and then plot it, so around 0 it will be having a very high value, and after that it will just get reduced. So, basically if I say m square t multiplied by this particular thing, not the actual spectrum, will actually go over to omega ct, right. So, even if I never had anything for mf, I will now be having something. Not only that, by squaring I ensure that that gets convoluted. So, it will be having a peak over here which is expected. I want most of the power around the center, because that is where I will be extracting my carrier. This is just for carrier extraction. Remember, this is not the signal demodulation. I will take that part, I will just tap some power from there and I will try to actually extract carrier from here, right. So, that is what I am trying to do. So, of course, I can always do that. I can multiply with this, means I can actually square this. Squaring is possible, any nonlinear circuit you can employ, you can get square of that. So, and after that you just put a band pass filter around that. Now, you do not have to for sure know the FC, what is happening, because it will have a sharper peak. So, if you give little bit of extra band, it will actually pick that frequency, that is the major frequency component. So, it will pick that frequency. Not only that, because this carrier is already there, so 2 omega ct, whatever phase it has and whatever frequency it has, it will take that. So, all you have to do is you have to put a band pass filter and then average it, okay. The amplitude has to be averaged. So, from there the carrier information is already coming over there. So, m square t has nothing to do with it, okay. So, you will be getting the extracting the carrier information if you do a squaring, right. So, that is pretty nice for DSB-SC. I can see that even if it does not have any DC component, even if I modulate it, I do not get anything around omega c, but if I square it, I will be getting something which is exactly mimicking the input phase and frequency, because this 2 omega ct, if there is a drift in omega c, that drift will be reflected over there. So, I will be getting same drift over there. If there is a drift in phase, that will be reflected over this 2 omega ct. Whatever is coming, I am actually squaring that only. So, that will have exact same frequency and phase, and if I put a band pass filter, it will just extract that thing, okay. It is not becoming 0, because m square t is no longer 0 over there. So, I will get some amount of signal at 2 omega c. All I have to do is, if I need to get omega c, I have to half the frequency. There are frequency, means this divider and all those circuitry are already available. So, if I get 2 omega c, I can always create omega c from that. That is not a big problem. There are circuits where frequency halving is possible, okay. You can immediately with a comparator convert it to a digital signal with 1 and 0, and then you can do a frequency halving by any counter and all those things, okay. So, that is pretty much possible, that is not a big problem. So, that I can do, then whatever I get, that is exactly synchronous to incoming phase and frequency, okay. So, this is a technique. Whenever I do a squaring, I will get my frequency back. We will see also there are some more things which will be the discussion of our next class probably, that is called phase lock loop. We will come back to that, but right now we should be pretty happy with this, that we can at least extract the carrier. Now, let us discuss if it was a SSB signal, can we extract the carrier? DSB we can see. Now, let us see, we have a SSB signal. So, let us say we call that VSSB, okay. So, if I have the carrier, so VSSB t, so that I can write as mt cos omega ct minus or plus, I can take one of them for upper sideband or lower sideband. So, mht sin omega ct, that is the representation of SSB, okay. VSB also will have similar representation. So, we will see similar things will be happening in VSB, okay. So, now I can represent that in a similar fashion as we have done for envelope detection of VSB with carrier. So, I can represent mt and mht as some et into cos some theta t and et into some sin theta t, right. I can write that. So, immediately I will be writing et this as cos omega c t, depending on plus or minus, I can write that as theta t, right. If this is minus, it will be theta t, if this is plus, this will be minus theta t, right. So, I get this VSB can be represented as this. Now, if I just square it, it is all about squaring. Earlier we have seen with squaring we are getting things. So, now you square it. So, VSB t, you square it. What do we get? We get e square t cos square omega c t plus or minus theta t, right. Take half e square t, I get 1 plus cos 2 omega c t plus theta t, right. I do get this. Now, this is around 2 omega c. So, if I just put a narrow band pass filter, I will be getting this thing. So, what we are getting? Again narrow band pass filter, the carrier that we are getting, that is not 2 omega c t, it has some modulated part which is not the pure carrier. Okay. Earlier I was getting the carrier back for DSB SC, I was getting the carrier back, fortunately. I was getting just 2 omega c t. If it has a drift, I was getting 2 omega c t plus theta. But now I am getting some theta t which is actually determined by this mt and mht, which is coming from the message, and that will actually change. This is not a pure cosinusoidal now, this is something else. So, that I cannot take as a carrier signal, because it is a corrupted carrier signal which is not a pure cosinusoidal. So, whatever I do, even after squaring, I do not get my carrier back. Okay. I can employ a band pass filter around 2 omega c t, but whatever I will be getting, that is not actually a carrier for me. So, with that I will not be able to employ any demodulation. So, that is why you can see for VSB also same thing will be happening, because this will be instead of MH, it will be MV after passing through that filter, right. So, again there will be some theta term in the carrier if you try to square it. So, you will never be able to through a narrow band pass filter extract the carrier from there. So, that is why if for SSB and VSB, if we wish to demodulate it without carrier, that is not possible. First of all, you will not get carrier back. So, all you will have to do is you will have to send some carrier along with it. So, that is where it becomes power inefficient, because we have already seen that if we just try to put some power for VSB, if we wish to do envelope detection, then we will have to actually put huge amount of power to employ that envelope detection. Of course, it can be proven that for VSB the power will not be that high as compared to SSB, but you will have to put power which is very high compared to our amplitude modulation that we have employed. So, that is pretty much the discussion from engineering point of view, from modulation, demodulation point of view, that what happens in different kind of modulation. They have some advantage, some disadvantage, we have explored that, and now we are in a position to actually explore more on carrier recovery, because we have already seen anywhere we wish to employ coherent demodulation, we have to have some nice carrier recovery circuit. We have already for DSB-SC, we have already told that maybe squaring might give me a carrier, but we will try to make that even more accurate. So, that is where the PLL circuitry will come into picture, which is called phase locked loop, that has a big importance in communication system. So, we will try to now explore the PLL circuitry from next class onward. Thank you.